Good afternoon, everybody. Welcome to a cold but sunny Monday afternoon at Chem 170 Organic Chemistry with your host, me, Dr. White. Got a couple things I need to talk to you about. First of all, hopefully you all have a very happy Thanksgiving this Thursday. Yes, we will have class on Wednesday. Now, technically, I don't have to have my office hour because it's after 5 o'clock on Wednesday when the school officially shuts down. However, I will have my office hour from 5 to 6. If anybody needs any help, stop by. All right, that's one thing. So we will have class on Wednesday, but I also, which I don't have to, I'll have my office hour. I'll also have it tonight. Now, a couple important things. Coming up a week from this Wednesday will be test number 4. Again, a week from this Wednesday, not this Wednesday, but a week from this Wednesday will be test number 4. Now, the Monday before that, a week from today, I'll be having my other cataract eye surgery on my right eye, this one. This is getting back. I put my eye drops in too late. I should have done it earlier, but I was busy. But anyways, so I will do what I did last time. I will make up a video that I will post on YouTube with the review for test number 4. And today and Wednesday, I'll finish up carbohydrates. On Wednesday, I'm going to do the fats and oils problem set. Next Monday in the videotape, I'll go through the carbohydrate problem set. And because next Monday, I will not have office hour after the operation, what I will do, and I'll put out an email to this effect, a week from tomorrow on Tuesday, I'll have an office hour in case you need help. Same time, but on Tuesday, same login. So if you need extra help for the test on Wednesday, stop by. And now for something exciting. Ooh, let's do the exciting thing. That's exciting, but that's not what I want to talk about. If you go to the assignment area, I shall turn it on so you can see it. Everybody see? Thumbs up, people. Do you see? Thank you. I don't even have to say anything. You guys can read my mind. Thank you. If you go to the assignment area, you'll see, oh, look, extra credit project. What is that? Well, first of all, let me back up because I'm in faculty view and I need to go to student view. Go to assignments. And you will see extra credit project. This is an optional project, but let's look at it. Everybody see extra credit project on your screen. It's 10, yes, 10 bonus points. And how do you get those 10 bonus points? By creating a chart that contains 10 organic molecules, which are found in the ingredients list of commercially available products. In other words, things you can buy for your daily life. You can use a molecule only once in a chart, but you can get up to 3 molecules per product. Dr. White's being sneaky, going to make you look at a couple of things. And to get full credit for that molecule, which is 1 point, all entries in a row of a chart must be correct. For each entry, record the name of the product, the name of the molecule, and one of the functional groups. If there's more than one functional group, or if there's only one functional group, the only functional group that's present in the molecule. Be sure to put your name on the chart. All right, here's an example of how it should look. First column, product. Second column, molecule. Third column, functional group. And I put down brand X wine contains ethanol, which is an alcohol, and you'd get 1 point. To get 10 points, you have to have 10. Makes sense, but I've had students, how come you only gave me 7 points? They were all correct. Well, you only had 7 entries. You need 10 to get 10 points, 1 point per entry. Now, to make this interesting, you cannot use, now the molecules you can't use are sucrose, ethanol, isopropyl alcohol, or 2-propanol, same thing, acetone, ethyl acetate, propane, acetic acid, or methane. The products you can't use are beer, wine, vegetable oil, vinegar, gasoline, propane gas, natural gas, orange juice, milk, sugar, or butter. Everything else is fair game. Now, note, this is important. Ingredients must appear, excuse me, on an ingredients list of the product. You can't say a banana has this ester in it, because I have yet to see a banana you can buy that has an ingredients label on it. If you find one, let me know. I'd be interested. And this is important. They must contain a functional group discussed in this class. There are a lot of other functional groups I have not talked about. And whenever a student tries putting one of those down in the past, they always get it wrong. So to stop that, I only limit it to the functional groups we've talked about this semester. You know, things like double bonds, triple bonds, benzene rings, alcohols, thiols, ketones, aldehydes, carboxylic acid esters, carboxylate anions, amines, amides, and quaternary ammonium salts. I think I got just about everything there, and ethers. Now, this is due by the end of December 8th, and no late projects will be accepted, period. You have to get this in on time. And please upload it as a PDF file or MS Word file. Now, here's something important. Beware, not all names on labels are IUPAC or common names. And you see the word or the product or compound simethicone, you say, oh, O-N-E ending, it's a ketone. No, it's a silicone product, which we haven't talked about silicone functional groups in this course, and we won't. So, and there are others like that. Now, how do you find out what functional groups are in the molecule? Well, go to Google, put in the name of the ingredient or molecule, and then put chemical structure. One of the first 3 hits that come up on your Google search will have the chemical structure. And you've all learned how to play that game, circle and name the functional group. And you'll be able to identify, at least I hope you can. Now, the other thing that I will do as a public service to all of you, and that is before you hand in your project, email it to me. I'll check it over. If there's anything wrong, I will tell you so you can correct it. And there's no reason if you hand in the project that you shouldn't be able to get 10, yes, 10 bonus points. Yes, I have 5 fingers on each hand, so that adds up to 10. And think of this way. It's like adding 10 points to your total, or another way of thinking is adds 10 points to any one of your test scores, which can never hurt. Now, this is an optional project. You don't have to do it. But if you do, you can get 10 points. Now, let me show you how easy it is to do. Again, to get your 10 points, you need 10 different molecules from, and you get 3 per molecule per product, you'll need 4 different products or items you have to look at. Now, important thing that sometimes students get in their mind they have to do, you can have a table where every molecule is an alcohol or a ketone or whatever. They don't have to be 10 different functional groups. They just have to be 10 different molecules. And they have to come from, you can only take 3 molecules per product. Now, remember, they all don't have to be different functional groups, but they do have to be different molecules. So you could have 10 alcohols. I had a student who did that. All right, let's take a look at how easy this is. It's going to be winter. It's just about winter. And in the dead of winter, when I've been out shoveling snow and all that and whatever, walking to my car and back before the pandemic, my lips would get chapped. And a great product I've been using for many years is Carmex. And if you look, it's got an ingredients label, which you probably can't focus in on. But I'll read one of them, phenol. And there are 2 different functional groups in phenol. One is an alcohol, the other is a benzene ring. So you could put down Carmex, phenol, and either alcohol or benzene ring, and you got your 1 point. Oh no, I just gave you 1 point you could use. You can use that if you want. And if you look at the ingredients label, there are 2 other molecules you can get from here. Now, where can you find stuff that's easy to use? Just go into your bathroom and look at some of your personal care items and things you use for your general hygiene. Also, go downstairs and open your refrigerator. That's the way to do it. Now, if you really want to have fun, go to your local supermarket or big box store and walk down the personal care items or any aisle with condiments. And within 5 minutes, you'll have a list of 10 items from the 4 different actually products. But remember, it has to be on an ingredient list. You can't say, oh, I know there's thiol and natural gas. We can't use that anyway, so that's a TBO thiol, but you can't use that. But also there's no ingredient list on there. So that's it. If you have any problems, ask Dr. White. I'll be more than happy to explain and help you answer any questions you have. And like I said, email me your list before you upload it to the assignment area, and I'll tell you what's right or wrong, and you can go back and correct it. So you should be able to get 10, yes, 10 points. Any questions on that from anybody? In case you forgot, due to the outstanding work of my eye surgeon, Dr. Cabin, it looks funny. No lens, because I don't need it in this eye anymore. All right, let's get back to work. We were doing work, but let's get back to carbohydrates. Now, I talked about chiral and achiral objects. Well, let's move on. Now, there's something in a molecule or molecules called a chiral center. And the switch is on now. I'm never going to ask you what is a chiral center, but it's an atom in a molecule that has 4 different groups tetrahedrally bonded to it, which means in this class, we're going to talk about a carbon. Now, if you think about a tetrahedron, A and B are in the same plane, but this little wedge for C says it's coming out towards you. The E with the dotted wedge or dashed wedge means it's behind the plane going away from you. And that's 3 dimensions. And right now, I don't have my models as, well, I have one. time out while I build something for you. And if we were in a classroom, you'd see me doing the same thing. In a classroom, we can see it better, but let's see how this works on Zoom. All right, here's a carbon in the center, and it has a silver post, black post, red, and yellow. And notice how in the plane, the silver and black are in this plane going through the molecule. In this plane, notice how the yellow is coming toward you. And the red is behind that plane. And this would be the wedge yellow, the red dash wedge. Now I have a similar looking molecule, but they're mirror images. Silver on top, black, yellow, yellow, red, red. And they're non-superimposable mirror images. Carbon to carbon, silver, silver, black, black. Oh no, these are not lined up. Same thing here. And if I go, okay, I'll line them up. Red, red, yellow, yellow. Now the black and silver don't line up. So they're non-superimposable mirror images. Yes, those are chiral molecules or objects, and in this case, they're molecules. Now, where that plays a very important role, first of all, I won't ask this on a test, but this is talking about stereoisomerism, isomers that have the same molecular and structure formula, but different orientation and space of the atoms. And isomers whose atoms are connected the same way, another way, but different arrangements in space. And to have a stereoisomer, you need a chiral center, or for this case, I'll call this a chiral carbon. And it's got to be rigid. Now, an amine and a quaternary ammonium salt are not rigid. How many of you have ever been out in a windstorm with your umbrella? All of a sudden it goes whoop and goes the other way. The wind pops it and inverts it. Well, nitrogen in a quaternary ammonium salt can do that like an umbrella in a windstorm, and you can pull it back down, and I've done that. And that's why that's not considered a chiral center, where a carbon atom, nope, this isn't going to invert like a quaternary ammonium salt will. So what does this lead us to? The following. I thought I opened it. I guess I didn't. 1 second, please. Maybe more than 1 second. Let me just get rid of this. And now I opened it. All right. Sorry about that. The joys of working on Zoom. Everybody see 3 points each on your screen? Thank you. Now, a lot of this was on the videotape I put on last week when I wasn't here, but I still like to recover it. All right, let's look at 3 points each. Circle the chiral carbons in the following molecules. All right, now for that molecule, I'm going to take some water while you copy it down. How do you know where there's a chiral carbon? Well, a chiral carbon has to have 4 different groups or 4 different atoms or a combination of 4 different groups and atoms. If it has 2 or more of the same atom or group on that carbon, it cannot be chiral. If a carbon has 2 or more of the same group on a carbon, it can't be chiral. So if we look at this carbon, it has 3 hydrogens, it's out. If we look at this carbon, 2 hydrogens, it's out, because you need to have 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. If we look at this carbon, it has 2 hydrogens, it's out. And this last methyl group, CH3, 3 hydrogens, out. So that leaves us with this carbon and this carbon to consider. Let's consider it. It's got a bromine, this carbon, a hydrogen, a methyl group, and all this I'll call R. So methyl, R, hydrogen, bromine, 4 different groups, 4 different atoms, or combination of 4 different groups or atoms. So that would be circle. Now, if we look at this carbon, it's got a hydrogen, hydroxyl group, a methyl, and this right here, I'll call R, it's different. So hydrogen, hydroxyl, methyl, and this whole rest of this. So it's got 4 different atoms or groups or combination. Therefore, I'm going to circle it. Now, let's look at something else. All right, I'll give you time to copy that down. Remember, tonight at 5 to 6:15, I'll have an office hour. If you need any help with anything, stop by. Don't forget, hand in your labs this weekend. I caught up. Sorry, I got behind a week. I can blame it on my eye surgery. Not really. I just forgot to upload the grades from the second to last lab. Oh, what the heck? I'll blame it on my eye surgery. All right, let's look at this one. I'll do this one. Then you know I'm going to share. How do you know to circle a chiral carbon? It has 4 different groups or 4 different atoms or a combination of 4 different groups or atoms. If it has 2 or more of the same atom or group on it, it won't be a chiral carbon. So this has 3 hydrogens, that's out. All right, now it has to have 4 different groups. This carbon and this one double bond only have 3. If you have a carbon in a double bond or triple bond, it's out. Oh, look at the carbonyl carbon. It's in a double bond to oxygen. So that's out. So we only have these 2 carbons to think about. Wasn't that fun? Easy, quick? Yes. So if I look at this carbon, have a hydrogen, a thiol group. This group I'll call R, and this group I'll call R prime. And notice hydrogen, thiol, R, and R prime. That's 4 different things, combination of groups and atoms. Therefore, I will circle that carbon. And next, I'll look at the next carbon next to it. And we have a hydrogen, a chlorine. This group right here, I'll call R. And this whole thing here, I'll call R prime. So if we look at this carbon, hydrogen, chlorine, R, that's awful looking R, and R prime. So it's 4 different groups or atoms or combination thereof, and I'll circle it. And that's how you determine a chiral carbon. And a molecule, to be a chiral molecule, remember chirality means handedness, must have at least 1 chiral carbon. All right, there's something for you to have fun with. Circle the chiral carbons in the following molecule. Ooh, don't look yet. I forgot a hydrogen. Now you can look. Thank you, Megan. Everybody else, I'll wait until you give me a thumbs up. Thank you, Joe. Thank you, Yesenia. I hope I'm pronouncing everybody's name right. If I'm not, either send me a chat message or open up your mic and say, no, this is how I pronounce it. All right, let's take a look at this one. How do we know what carbons are chiral? Well, the easiest way is to eliminate those that aren't. If we look at this carbon, 3 hydrogens, it's out. This carbon, 3 hydrogens, it's out. Now let's look at this carbon. Oh, look, it's got 1, 2 methyl groups, so it's out. If it has 2 or more of the same group or same atom, it's out, can't be chiral. Well, this one looks good with the hydroxyl, so I'm going to leave it alone. Oh, carbon and double bond, another one, those are out. But carbon is in a double or triple bond, it can't be chiral. This one with the iodine looks interesting, so I'm going to leave it. And the next carbon right here has 2 hydrogens, so it's out. Here we have a carbonyl carbon, carbon double bond, it's out. And finally, this last carbon has 3 hydrogens, has 2 or more of the same group or same atom, it's out. So if we look, we only have, that was quick, this carbon to consider and this carbon. And if we look at this carbon, it has a hydrogen hydroxyl group. This I'll call R, and it's different from this R prime. So it's got 1, 2, 3, 4 different groups or atoms, or in this case, combination. So it's chiral. And if we look at this carbon with the iodine, right here, it's got a hydrogen iodine. This group I'll call R. This group I'll call R prime. So you have hydrogen, iodine, R, and R prime. 4 different groups, 4 different atoms, or in this case, a combination of 4 different groups and atoms. So that would be circle. Oh, let's do one more. And there's the one more. Circle all the chiral carbons. This is a tough one. Let's see if you're up to it. Thank you, Megan. Thank you, everybody else, Joe and Yesenia. All right, let's take a look at this. And the way I like to approach this is, are there any I can eliminate quickly? And this methyl group has 3 hydrogens. This methyl group has 3 hydrogens. If you have 2 or more of the same atom or group on a carbon, it can't be chiral. Now this carbon here has a double bond. If a carbon is a double bond, that's out. Now, one of the things you forget, but each one of these carbons in the ring that I've shown has 2 hydrogens, CH2. So this would be out, this would be out, this would be out. So now we have this carbon, and this carbon to deal with. And remember, on this carbon, there's a hydrogen and this carbon. Now, let's do this carbon right here, bromine, hydrogen, methyl group, ring, chiral. Let's look at this carbon right here. Hydrogen, methyl, this part of the ring, and this part of the ring, which would be R and R prime. They're different. And therefore, that would be a chiral carbon. And finally, this carbon right here, hydrogen, this group I'll call R. And then let's go to a different color. I can say this part of the ring, I'll call R prime. And this part of the ring, all this, I'll call R double prime. So if we look at this carbon, I have hydrogen, R prime, R triple prime, 4 different combination of group of atoms, and therefore this has 3 chiral carbons. And that's an important thing. And the reason why is that tells me this molecule is chiral. It has a non-superimposable mirror image. Now, when we're talking about molecules, there's an important term you should know, and that's enantiomers. And I think I'll be subtle today. Wink, wink, hint, hint, say no more. That comes from Monty Python. Now, enantiomers are molecules with non-superimposable mirror images. So this is glucose, and you don't have to memorize it, but I'm going to go to the whiteboard and use glucose. It's one of those words, organic chemistry, I always spell wrong. So I'm going to cheat. And now I can see I was about to spell it. Well, I might not have. Now, this is called the Fischer projection of glucose. And let me talk about Fischer projection. I think I have it later on in the slides. So let's go back to my slides. That's not where I wanted to go. Let me just do something real quick here. And I should have put this earlier. All right, everybody see Fischer projection on your screen? Thank you, Megan. All right, now Fischer projection was created by the great German organic chemist Emil Fischer. He was the one who also did Fischer's esterification. And what he figured out is you have a three-dimensional molecule. Let's assume E is red and C is yellow. If you rotate it 90 degrees and flatten it out, you can write it like this. Now, A and E are coming towards you. D and A are coming back behind a piece of paper. So this shows 3 dimensions in a quick 2-dimension thing. Now, this is a Fischer projection. Now, one of the things you can't do is just pick it up. And what I'm going to teach you now is how would you draw the mirror image for this molecule using the Fischer projection. Now, I like to draw in my mirror. You don't have to, but this is the mnemonic device that helps me. Now, if we have a mirror, like you hold your left hand up, what are you going to see first in the reflection? What's closest to the mirror? My palm. Well, what's close to the mirror? E. So I'll see that. What's farthest away? C. What's on top? A. What's below? D. Now, these are mirror images. These are also called enantiomers. Enantiomers, sometimes called enantiomeric pairs, are the mirror image pairs of something that's chiral, which this molecule, let's call this Roman numeral 1, and it's enantiomer Roman numeral 2, for those who know Roman numerals. If not, 1, 2. And well, you can say, can't I just rotate this 90 degrees? And the answer is no. These A, E, and C are coming towards you. As soon as you rotate it 180 degrees, C and E will be going back, where in this case, C and E are going forward. So the only way you can tell with a Fischer projection if they're non-superimposable mirror image is if you just pick it up as it is and lay it over the other, which in this case, E and C would not line up. So if we look at this problem, draw the enantiomer 4, and what this really means is draw the mirror image of the molecule I give you. Now, if I were cruel, which I don't, I'm not, I could put down a test a molecule that's achiral, and you would have to say, oh, guess what? It's got a superimposable mirror image, and therefore I can't draw. If I ask you to draw the enantiomer, it has a non-superimposable mirror image. Therefore, what do? Yeah, I like to put in my mirror. Now, this carbon here and this carbon are achiral. You can draw it with the oxygen like this, or I'm lazy organic chemist. I'm just going to draw it like this. Oops. Remember, this is another way of writing an aldehyde, and my software for sugars does that. All right, now if we look at the bottom carbon here, that's chiral. It's got 2 hydrogens. Why is this one chiral? Because it's an achiral carbon, because it's in a double bond. It's not a chiral carbon. And the same thing here. Therefore, you really don't have to draw the mirror image. But now, remember, each line intersection is a carbon. If we start at this carbon, which I'll call 2, because carbonyl carbon is 1, 3, 4, 5. If I look at carbon 2, what's closest to the mirror? The hydroxyl group, I'll see that. What's farthest away? The hydrogen. I go to the next carbon, 3. What's closest to the mirror? Hydroxyl group. What's farthest away? Hydrogen. Now, if I look at carbon 4, what's closest to the mirror? Hydrogen. What's farthest away? Hydroxyl group. And finally, carbon number 5, what's close to the mirror? Hydroxyl group. What's farthest away? Hydrogen. And those are not superimposable. They're non-superimposable mirror image. So this is the enantiomer. Of glucose. And glucose is an important sugar we'll talk more about today. Your turn. Draw the enantiomer of this molecule. Thank you, Yesenia. That means draw the mirror image of that molecule. Shh, don't tell the instructor I helped. Thank you, Joe. And thank you, Megan. All right, how do you draw the enantiomer of this compound? Draw its mirror image. The aldehyde, I can draw like this. Do you want to draw it like this? That's fine. This group, I can draw like this. If you want to draw it like this, oh, excuse me. That's fine, but I won't. And now we look at carbon 2 and 3. Remember, carbonyl carbon is always 1. And therefore, what's closest to the mirror hydrogen, what's farthest away, hydroxyl group. Remember, each intersection of a line is a carbon. Next, carbon 3, what's closest to the line or mirror hydroxyl group, what's farthest away, hydrogen, and this would be the answer. And that's how you do enantiomers. If I look at the clock, it's time for a break. With that, let's take a 5-minute break. I'll see you at 1:55, and I'm going to go stretch. I'll see you in 5. Time to get started. All right, I was talking about enantiomers. Enantiomers are non-superimposable mirror images of a molecule and or enantiomeric pairs, and therefore, well, your hands are non-superimposable, they're a pair, but they're not molecules, individual molecules. They're made up of a lot of molecules, but anyways, so if I ever ask on a test, draw the enantiomer of this molecule, what do? Draw its mirror image. Now, when a molecule has more than one or more chiral carbons for this class, instead of chiral centers, I'll say chiral carbons, it is chiral. It has handedness. Now, here again, we have glucose. And the first thing I'm going to ask you before I talk about chirality of monosaccharides is ask you on glucose here, circle the chiral carbons. Why don't you go ahead and circle the chiral carbons? Remember, every intersectional line is a carbon. Thank you, Megan. Thank you, Sonia. And thank you, Joe. Now, if we look at this first carbon, it's in a double bond. It's carbonyl, it's out. And this bottom carbon has two hydrogens, it's out. But this carbon has a hydrogen hydroxy group aldehyde, and below it an R group. It's chiral. Same thing here, same thing here, same thing here. So these are all chiral carbons. Therefore, glucose is chiral. It has a non-superimposable mirror image. And because of that, organic chemists came up with a naming using Fischer projections to help name certain chiral carbons. Now, in an aldehyde, the carbonyl carbon is 1. This is 2, 3, 4, 5, 6. Now, there's a letter designation you call DL. And this D is for dextrose, L, I believe, lavatory, I'm pronouncing it correctly, right and left in Latin. And if we look at carbon, the switch is off, but for other classes, you might need to know this. So that's why I'm talking about it with the switches clicked. I'll never ask on a test. If the hydroxyl group on the highest chiral carbon, which is 5, is on the right, it's called D. If it's on the left, it's D. If it's on the left, it would be L. And let's go out into the real world. It used to be called Aldrich, and then a sigma bottom out, so, and it's called SigmaAldrich. And this has been for many decades one of the best companies to get small quantities of chemicals. Small meaning anything under a pound or 2 pounds. And if you look on here, notice they have dextrose, but underneath synonym, let me click on this, we have D plus glucose. And D-glucose tells us, this is another form I'll explain in a little while, that hydroxyl group is on the right. Switches off, this won't be on a test. So let's continue. Now, when we talk about chirality, when we talk about enantiomers, non-superimposable mirror image molecules, they have the same physical properties, same melting point, same color, they smell the same. There's only 2 differences. Switches off, but this is important. You should know for other classes. One is optical activity. The second one is reactivity with other chiral molecules. Now, what's the optical activity? Optical activity, optically active compound, which enantiomers are compounds that rotate plane polarized light. When you're looking at the light from the sun or my light bulbs that I have up here, it's giving off white light. And the waves, light can be a particle or wave. It's coming like this, like this, like this. All 360 degrees are coming at you. Now, scientists have a way of filtering out all but one wave. So it's coming like this. And we call that plane polarized light. How many of you have ever seen the polarized sunglasses? That do a good job because they cut out almost all the waves except one coming to your eye. Now, with a light source and a plane polarized light, when it goes through a solution of a chiral compound, if I had a detector here, it can detect, has that one wave still coming like this, or has it rotated right or left? And when something is started, should be like this, rotates, you can measure the angle. I ran out of hands and fingers. And that's one key property of optically active enantiomers. They rotate plane polarized light different ways. Now, interesting story. Who was the first one to separate a mixture of enantiomers into separate piles of this DNL? Louis Pasteur. And he did that with a compound called tartaric acid, because you could see the crystals were mirror images. So at a microscope and tweezers, he was separating it. Brilliant work, must have been tedious as heck. Now, the other thing that enantiomers differ in, non-superimposable mirror image molecules, is how they interact with other chiral molecules. Now, if you think about it, let me see if I do. This is my house key I carry around. If I put the key in upside down into the lock, it won't go in. I have to have it oriented properly. Well, same thing with molecules. They have to mesh up right, because if they go like this, they won't, and they won't interact. And your body has a number of chiral molecules, a lot of them, that have to be the right enantiomer for it to work. That's part of the reason why certain drugs are very expensive. You have to have the right enantiomer, which can be expensive to make. Now, switch was off for that also. And like I said, there are two types, dextrorotary and levorotary. And in the name, if it rotates plane polarized light to the right, they put a plus sign. If it rotates to the left, the minus sign. If you remember, what I showed you was D plus glucose, and that means A, D tells you the hydroxyl group in a Fischer projection is on the right, and the plus tells you it rotates plane polarized light to the right. Now, one of the things, knowing the structure, there's no way you can predict, is it plus or minus? You just have to go in the lab and measure it. All right, let's get back. All that was in chapter 5 of our book, which I skipped until now. And now let's go back to our carbohydrates. Now, there's different classifications. And let's talk about, and the switch is off now, but again, for other classes, you may need to know this, and that's why I'm covering it. For monosaccharides, polyhydroxyl monoaldehyde or polyhydroxyl monoketone, they have what's called aldoses. And I'm not a sugar chemist, or carbohydrate chemist. Why they had to come up with these names, I don't know, but they did, and people use them. And a monosaccharide that contains an aldehyde, which glucose is called an aldose. And if it's 6 carbons, it's called a hexoaldose, but we're not going to have that ever on a test. Now, if it has a ketone, and this is fructose, notice I have a ketone, carbonyl, carbons, carbons. This right here is my carbonyl carbon of a ketone. And these are called monosaccharides that contain a keto group. It's called a ketone or ketose. And how many of you ever heard the term ketosis? And that's a problem. People are diabetic, and it deals with sugars in your blood, mainly ketones. Now, interesting story. About 3 years ago, one summer, I had 2 students, both who were diabetics. How did I know that? Because they had the new insulin pumps on their, right above their elbow. And it was summer, so they had short sleeve tops on, shirts or tops. And second of all, when I teach face-to-face, I ask students to privately see me. If you have any kind of serious medical condition, I like to talk to you, because if you ever have a medical emergency, let me know how I should deal with it. And that's always important. Years ago, I had one student who unfortunately didn't have medical insurance and was epileptic, and said, if I go into a mild seizure, don't call the paramedics because I don't have the money to pay them. And thank God their student didn't go into seizure in my class, and I hope nobody's. But anyways, that's how I knew I had 2 diabetic students, because they told me about it. And also what to do if they had any problems. Now, just to remind you, a sugar is the general designation for a mono and disaccharide, and therefore glucose, fructose, and sucrose, which I talked about, and this you should know, are sugars. All right, let's talk about D-glucose, then I'll explain in a little while about this right here. But D-glucose, just out of curiosity, I don't know if you know, it's the most abundant sugar in all of nature. And that's the sugar in your blood that helps keep you alive. Now remember, I'm an organic chemist, and the last biology I had was freshman year of high school. Well, that was a long time ago. And it's called the aldohexose, which means an aldehyde with 6 carbons as a sugar. And it turns out it rotates plane polarized light to the right. None of this you have to know, but I thought I'd mention it. Now, D-fructose is a ketohexose, ketone with 6 carbons. Turns out fructose is the sweetest sugar available. It's, I don't know how many X times sweeter than glucose or sucrose, table sugar. And it rotates plane polarized light to the left. This will never be on a test. And it's found in corn syrup. And if you go to look at things like ketchup or other foods, you'll see or biggest one I can think of is pop, and you'll see water, then you'll see corn syrup, or they'll say fructose or corn syrup fructose. And about 20 years, maybe a little longer, organic chemists showed the food companies how to make, or they worked for them and found out how to make high fructose corn syrup. And it was a lot cheaper than sucrose, table sugar, to sweeten things up. And so it's cheaper, you need less because it's much sweeter. And therefore, most food groups have, or items to sweeten, use the fructose from high fructose corn syrup. And this can form a cyclic form too. Now, what this form right here and this on the right are called Hawthorne projections. Take a deep breath. This will not be on a test. Take a deep breath. And whenever I ask students to do Hawthorne projections, see, it's even on the slide, not on the test. It's a two-dimensional structure notation that specifies three-dimensional structure of a cyclic form of a monosaccharide. And whenever I had students try and do that on a test, I think 2 years in a row, not one student got that problem right. I said, you know something, I'd rather spend more time on other things. And I came up with a good idea how to bypass that. All right. Oh, it's not in red. Sorry about that. Are you seeing double? Let's try this again. Now here we have glucose. And this is a cyclic form of glucose, and it's in equilibrium and this is very important, because if this reaction didn't happen, we wouldn't have any starch, we wouldn't have any trees, we wouldn't have any plants. I'd say that's important. Let's talk about this reaction. And I go to my whiteboard. Now, I promised no new reactions. So let me remind you of something. For test number 2, you learn for an aldehyde or ketone, when R prime is H, it's an aldehyde. When it's carbons, it's a ketone, reacted with an alcohol and an acid. What's attached to the carbonyl carbon is still attached to that. And then the alcohol forms this. And this, what was the carbonyl carbon, is now what's called a hemiacetal or hemiketal carbon. I don't think I said that when I taught you there. Now, let's look at glucose. And the carbonyl carbon, I'm going to draw like a carbonyl carbon. And here I have an aldehyde. Here on carbon 5, C5 is how we say it, I have an alcohol. Now, when two functional groups are in the same molecule, they'll react together real quick if they can. And therefore, this is called the intermolecular reaction. They're separate molecules. I need a catalyst, H+. When they're intermolecular in the same molecule, and by the way, I forgot something, sorry. Now it's there. They react and you don't need a catalyst. And you should know this. Now, how does this happen? This hydroxyl group is this hydroxyl group, which attacks and bonds to the carbonyl carbon to form this bond. Well, this attacks like that. Now, here's where I came up with a good idea to help students out. Instead of spending a lot of time and not mastering Hawthorne projections, I came up with the following idea, and it works quite well for students. Whatever is not reacted, I just rewrote. This carbonyl carbon is this one right here, which is this right here. This opens up to a alcohol, and then this oxygen right here is this oxygen right there. And here's what I came up with. Instead of having you learn Hawthorne projections, I came up with the world's longest carbon-oxygen single bond, all the way from that oxygen to this carbon. And this carbon here is this carbon here. And this bond right here is this bond right there. Because here's my alcohol, carbon oxygen from here and there. Therefore, if I give you the structure of glucose, and double equilibrium arrows, you should be able to draw that down. If I give you this, the hemiacetal cyclic form of glucose, you should be able, if I ask what's the starting material, you should be able to draw glucose. Go backwards. If this didn't happen, we wouldn't have a lot of things on our planet, including all the good things like Lay's potato chips, the onion sour cream, or French fries. I haven't had a French fry in at least 2 months. I need that like a whole lot. So let's go through this again. Here we have this hydroxyl group on a carbon, this alcohol. I have this aldehyde, which is this aldehyde. The alcohol, which you learned in test number 2, attacks the carbonyl carbon to form this hemiacetal, if it's an aldehyde, hemiketal, if it's a ketone you start with. Therefore, this hydroxyl group will attack this carbonyl the same way to form this carbon-oxygen bond. This opens up to this alcohol on this carbon. Everything else stays the same. And you should know how to do that. Now, if we go back, I'm going to ask you to think about the following. Which is easier to write? Dr. White's world longest carbon-oxygen bond method, or this? This is the same reaction I just showed you. This hydroxyl group attacks that, and this carbon right here is this carbon right here. This oxygen right here is this oxygen right here. Now, even I have to think about, I'm not a carbohydrate chemist. It takes me about 2 seconds. Oh yeah, that's right. But for you, if instead of having to go through the pain and again get it wrong, I came up with this way, which I think is a lot easier for you to handle. All right, now, turns out fructose can do the same thing. Here's the structure of fructose. And let me go to my whiteboard. Well, I haven't used this in ages. That means stop, new thing I'm going to draw. I used to do that in my notes all the time when I was an undergrad. And let's make sure I did this correctly, because this is one area of chemistry I really don't work heavily in and have in an industry. And the answer is I did. All right, now, same reaction, ketone or aldehyde plus alcohol, acid catalyst. This attacks here. That carbon, what's bonded to it, and this was from test number 2, is still bonded to it, opens up to an alcohol, and I have my O oxygen and the R from the alcohol. Now in D-fructose, or just let's call it fructose, we have, again, the same hydroxyl group on C5 is the same as this hydroxyl group of the alcohol. And here I'll draw in the carbonyl carbon. And this attacks that the same way this attacks that. And there's an equilibrium. When it's in the same molecule, you don't have to have a catalyst, which is why it's an equilibrium. All right, what's not involved in the reaction I'm rewriting. This is my carbonyl carbon, this one. Notice it'll have a hydroxyl group. And then this right here, this oxygen, again, this is easier for students than the Hawthorne projection, comes all the way here and bonds to that carbon. Let me clean this up a little. And this is a cyclic form, the hemiacetal form of fructose. And if this didn't form, we wouldn't have table sugar and some other things. So this is an important reaction. You should know if I give you this structure and show you this, and ask you give the organic product or product to write this. If I give you this and the double arrows and ask you to draw the starting material, or sometimes on a test, I'll ask also or put the name down. So if you want to remember, on the second carbon here, when you have the cyclic form, you start with fructose. On the first carbon here, when you have the cyclic form, you start with glucose. But if I give you the structure of fructose and glucose, you should know how to draw this. 3 points each. Let's go through this again. Here I have a hydroxyl group on a carbon. It's always carbon 5. Remember, this is 1, 2, 3, 4, 5, and then 6. Why? Because that gives the carbonyl carbon the lowest number if we're doing IUPAC names, which we don't. Nobody ever uses that for fructose or glucose. I'd have to think about it and actually sit down and figure out what is the IUPAC name, which I'll never ask you on a test. So this hydroxyl group is the hydroxyl group of this alcohol, which attacks this carbon of the carbonyl, which is the carbon on carbon 2. Everything else stays the same, except this hydroxyl group is this oxygen, and this is the world's longest and ugliest, but makes your life simpler, carbon-oxygen bond to this carbon, which is this carbon. And this is very important. So again, you should know how to do this. We'll practice it again on Wednesday. I'll probably have you practice it again in my video on Monday. Because if on test, I could give you fructose, double-headed arrow, give the organic product or product. Here it is. Or I can give you the cyclic form of fructose and double-headed arrow and ask you to draw, or if I was in a good mood, write the name, either way, of the starting material. This is very important. And is, like I said, which would you rather learn how to draw? This for how fructose cyclizes, or this how fructose cyclizes? I would have ventured to guess the second one is easier. But wait, I can do this. Anonymous poll time. Now, the question I'm going to send out to you says, are you done? But answer yes or no. Do you like the second way better for drawing the cyclic forms? Yes, you do. No, you don't. And remember, this is anonymous, so I don't know who's voting. Oh, I do. Everybody said yes. I actually knew that answer because years ago I came up with this, and it really has helped students at this part. All right, let's continue. Now let's talk about reductions. Oh, see, board. I better get to work. Now for test number 2, I taught you if you take an aldehyde or ketone, remember the carbonyl carbon double bond to oxygen has 1 pi bond and 1 sigma bond, just like a carbon double bond. Carbon pi bonds, you can break like that. Sigma bonds, no. So what happens here? You break the pi bond and each atom of the double bond gets a hydrogen. You make an alcohol. And you break carbon single bonds? No. Well, let's look at the following. Oh, by the way, on sugars, my hydrogens sometimes look mysterious. Like, what the heck is that? All right, I'm going to let you have some fun. Your turn. What's the product or products of the following reaction? Remember, this right here is really that. And one thing I should mention, does anybody here know of a reaction of hydrogen and catalyst with an alcohol? Because I don't, which means it's not going to react. And while you're doing that, and when you're done, give me a thumbs up. All right, everybody's done. Let's take a look at this. I have an aldehyde. It could have been a ketone. And when I react it with hydrogen and a catalyst, or the catalyst can be nickel, platinum, or palladium, in this case nickel, you break the pi bond and each atom of the double bond carbon oxygen gets a hydrogen. Well, you don't break carbon single bonds, and alcohols are not going to react with hydrogen in a catalyst. So all this stays the same. The only thing that will react is this aldehyde. And I could have also written this as CH2OH. Now let's take a look at this molecule. It has a name. And that name, common name, is sorbitol. And let's go out into the real world once again. If you look over here, here's on Wikipedia, every bend in the line is a carbon. 1, 2, 3, 4, 5, 6. Each one has a hydroxyl group. Now the wedge and dash wedge, salt and dash wedge tells you stereochemistry, which I'm not going to go into, but the dark wedge means it's coming towards you, that hydroxyl group. The dash means it's going away from you. And that's the structure when you get it. Now this is called sorbitol. And it's very sweet. And you can find it in various vegetables and fruits like apples, pears, prunes. Dr. White loves prunes. Yes, I do. And how is it made commercially? By glucose reduction. As aldehyde is converted to a hydroxyl group. How? Well, in real life, they used to have it here. I can't find it right now. It's used reacting with hydrogen in a catalyst. And that's what this first one is. Now, it turns out sorbitol, which is a sugar, sweet, is used a lot in over-the-counter things like cough drops and other cough syrups and other liquids, over-the-counter remedies. I didn't realize it was used in a laxative that can stimulate. That's interesting. You take your cough medicine and also have to go to the bathroom. I don't think I do, but whatever. But that's how they make it from glucose. Now, there's something very important. Part of the slide, the names, I'm going to turn the switch off. But the very last thing, remember the reaction with methanol. I'm going to turn the switch on and I'll explain why. Now, there's something called, just terminology. If you see this in your other classes, you can always come back to my slide or you know where you've heard it. A glycoside is the acetal or ketal formation of a monosaccharide. And the glucoside is the glycoside formed by glucose. Are you confused yet? Well, guess what? I think this would be a good time to take a break instead of rushing through this. Let's take about a 5-minute break, come back at 2:45, 5.5 minutes, don't tell the dean, and we'll continue on. Come back at 2:45 and we'll continue on. Oh no, I'm running late. Let's get going. All right, let's talk about a very important aspect of how monosaccharides become starches. Now, if you look at the slide, it says, remember the reaction of methanol. And that's a note for myself to remember the following. Now, a while ago, when we finished up the amides functional group, I said no new reactions. Well, I sort of fibbed a little, just a little lie. And let's remind you of a reaction you learned a long time ago for test number 2. If you take an aldehyde or ketone, when R prime is hydrogen, that's an aldehyde. When R prime is carbon, it's a ketone. And you reacted now with 2 molecules of alcohol with an acid catalyst. Keep your eye on the carbonyl carbon, what was attached to it. Ooh, there's something on my tablet. Is still attached to that carbon. And then the 2 alcohols, the OR, are attached to that same carbon. And this is a acetal or ketal, which I didn't ask you to learn. Now, what I didn't show you was the following. You learned before, one alcohol reacting with a ketone or aldehyde forms the hemiacetal. But notice we have 2 alcohols, and the second, this I'll never ask on a test, but I'll help you understand something important. The second alcohol reacts with the hemiacetal or hemiketal to form the acetal or ketal. Now, what I didn't teach you at the time to keep your life, how should I say, pleasant at the time or simpler, was when you have a hemiacetal or a hemiketal, and I will never ask those names on a test, instead of reacting this with the same alcohol a second time, I can react it with a different alcohol. And now I have a different type of acetal or ketal. Let's call this A. Let's call this one B. If you look at the 2 oxygens in A, the R group is the same. If you look at the 2 R groups on the oxygen here, they're different. And A is symmetrical, B is unsymmetrical. So that's important. If you have an hemiacetal, instead of making A the symmetrical and reacting with the same alcohol again, if you have a separate hemiacetal, you can react it with a different alcohol. And that's where the following comes in. This is the hemiacetal of glucose, which for this class, I like saying the cyclic form of glucose. And what it really is this hemiacetal. This carbon here is this carbon here. And if I react this with alcohol and H plus, just like you saw before, alcohol and H plus, this hydroxyl group will be replaced with this. And that's no different than what I had. Give you time to copy it down. Than what I had up here. This step right here. So if we look at the cyclic form of glucose, what does that mean when you react it with an alcohol and acid catalyst? This hydroxyl group is this hydroxyl group, and it will change to that. So everything else stays the same. And so I'm going to just copy it over. And I made a mistake, which I can erase right here. The only thing that will change is that becomes our triple prime. Turns out this is an important reaction. So let's have a repeat of this. I have this hemiacetal form, which is right here, reacted with an alcohol and acid. And here we have this, and I replaced the OH with OR triple prime. Everything else down here stays the same. I should put this in here too. So let's have some fun with this. And this one I will never give as a synthesis problem on test number 4 or the final. This is part of the semester where drawing structures takes a little more time. And I'll wait until you catch up. Anybody look at a bottle of ketchup? Ooh, there are some things you could use in that for the extra credit project. Oh, I'm giving away things. All right, let me do this one. What do we have here? This hemiacetal. This so happens R and R double prime are connected through the backbone of the sugar. It's in the cyclic form. Now, if I react this with this alcohol acid catalyst, the hydroxyl group on this carbon is replaced by the ROR group of the alcohol. Well, all this stays the same. So guess what? I'm just going to copy it over. So I've copied everything over. The only thing that will change, this hydroxyl group becomes this. What's our triple prime methyl? Oops. By this time of the semester, I have R on the brain. And that's what happens. And because I want you to, all right, everybody up to speed, what I just talked about, give me a thumbs up if it's okay to move to the next slide. Thank you. And the carbon with the hydroxyl group will be the carbon that the oxygen up here is bonded to. And it's your turn to have some fun. Remember, on Wednesday, I'll go through the fats and oils problem set because I don't believe I've gone through that yet this semester, so I will. Thank you, Megan. All right, let's move forward. Now, what do we have here? The cyclic form of glucose. And what does that mean? It means you have this hemiacetal. What's this? Hydroxyl group on carbon. That's an alcohol. And H plus is the catalyst. This is my R triple prime. And this hydroxyl group is replaced with OR triple prime. Everything else stays connected. So if that's the case, this part of the molecule will be unchanged. So I'm just going to copy it over again. And this hydroxyl group right here is replaced with that. Oxygen was R triple prime and propyl. And that's how you do it. I will never give a synthesis on this reaction on test or the final. Now, why am I spending time on this? And here's the fun part. Let's see, do I have a slide for it? Nope. Oh, I have to close some things. Let me close Word. Let me open Word again. I'm sorry about this. Anybody knows anybody who can, I don't know if it's I have too many things open. All right. Before I proceed, listen carefully. I'm going to be writing something down on my whiteboard. Do not, unless you absolutely have to, but you don't have to, don't copy what I'm going to write down right now. You don't have to copy into your notes. If we were face to face, I like that, special signals face to face. I would be telling the class what I'm going to put on the whiteboard. Don't write down, but it's something you should pay attention to. All right, let's get to work. All right. This will take me a little time, so be patient. In real life, you'd be watching me write this on the board. And even on a whiteboard, this is going to take me some time. Almost there, or almost finished. If you look now on the whiteboard, you see three structures, A, B, and C. All of them are identical. And if you look at those, They're all the cyclic form of glucose. Why did I do this? Let's look at A and B. If I take the following, and do this reaction I just showed you, if I take the cyclic form or the hemiacetal form of glucose, I'll replace the hydroxyl group on this carbon with OR triple prime. Well, here's that carbon. And if I react A and B with a little acid catalyst, otherwise known as a enzyme, let's look what happens. This hydroxyl group is this hydroxyl group. This carbon with this hydroxyl group is my OR triple prime. And now what happens is this now forms this bond, which is this bond. So we've now linked together by a chemical bond, single bond, A and B in an acetal formation. Now, if we look at B, oops, something fell off. Sorry about that. It has the same thing. On carbon C4, I have an alcohol, and this carbon up here, I have this hemiacetal hydroxyl group. Guess what? It can react like this. And notice I have formed a polymer. And if we look at C, if I had D, more glucose in a cyclic form, it would link together. I could go on and on and on like the Energizer Bunny. No, I don't have a big drum like that, but, and I guess I don't have big floppy ears, but it can keep on going. And let's take a look at this. A is bonded to B to C, and I could keep on going on and on. What that really is one glucose bonded to another, bonded to another, and it could go on and on and on. And when you have a lot of glucose molecules bonded together, and you should know this is called the starch. So in the cyclic form, glucose can bond together with this reaction to form starches and cellulose, things we use for food, things plants use to make plant walls. So you have trees, grass, all sorts of things like that. So let's do a reaction. What would be the name of the reaction product if I took 50 glucose and reacted with 50 more glucose? Your turn. Thank you, Megan. We'll wait a couple more seconds for Joe. Earth to Joe, come in, Joe. Thank you. I shouldn't pressure you like that. And the answer is starch. And that's how Mother Nature makes starch. And also, I'll teach you later on, cellulose by reacting glucose together. And it forms a polymer we call starch. Now, let's look at another interesting thing. If you have fructose in the cyclic form, which is the hemiketal, and you have glucose in the hemiketal or cyclic form, and you have a little acid catalyst, what happens? They link together, and this you should know gives you sucrose. If I can spell it. So fructose and glucose react together to make sucrose, table sugar. The next time you're putting sugar, table sugar, into your coffee, tea, milk, or on your cereal or oatmeal or whatever you put it in, or if you're baking, getting ready for Thanksgiving. By the way, I'll say it on Wednesday, but I'll say it now first. I hope you all have a wonderful Thanksgiving. It's time to teach you a new Yiddish word. How many of you have ever seen the tail of a turkey? You haven't? You know, the part that's sticking out from the end. And in Yiddish, the tail or your backside, your behind, is called a pupik. That's pupik. And my family, we love the pupik of a tail of the turkey. In fact, for many years, my brother-in-law and I used to start, I want a bigger piece. I want it. We finally came to mutual truce, and we both got same size. Actually, to keep him happier, I gave him a little bigger size because my job is to carve the turkey. I've been doing it for decades. Once you learn how to carve a turkey and you have sharp knives, which I do because my father taught me about those, and I have a really good set of Henkel 4-star knives. I think my set, which I bought individually, not as a package, probably right now to replace it, it'll cost me about $1,500. Yeah, they're good quality knives. But anyways, the pupik is the best. The other thing all of our family love is the skin. So instead of, she got a bigger piece, what we do, I came up with that idea, we take all the skin off the turkey, which is nice and crunchy the way my sister cooks it, and we cut it up so everybody gets the same amount, and no matter what kind of meat, because my family, most of the people like the white meat, but I also love the dark meat. But anyways, let's get back to chemistry. So if you react fructose and glucose together with an enzyme, H+, you get table sugar. This is something you should know. Meaning this and this. So I take a lot of glucose to react together with a catalyst, I'll get starch. If I take fructose and glucose and react together, I'll get sucrose. Now, let me remind you, what are these being linked together? They're this compound, which is really this, an acetal or a ketal. And starch is just acetal linkages of a polymer of glucose, which you see here. Now for sucrose, and I'll show you the cyclic form. Excuse me. Here on the bottom, this is the cyclic form of glucose. And this is a cyclic form of fructose. And this whole thing here is fructose and glucose linked together right here. And that we call sucrose, table sugar. So what does this all mean? Oh, by the way, polysaccharides, they contain many saccharides, this won't be on the test, linked together by glucosidic linkages, acetal or ketal. And we have another name for polysaccharides, and that's starch. Now, I have this, I won't ever ask on a test. Usually use carbon number 4 for the alcohol, and we make a starch called amylose, which is linear. Now, if you use also the hydrox group some of the time on carbon 6, the very bottom one, you'll get what's called a highly branched starch, and it's got a name, and I'll never ask on a test, amylopectin. Now, what does this really add up to? And the question is, what happens when you eat a starch, otherwise known as a carbohydrate? You know, the good stuff in life, like potatoes, rice, or even better stuff, French fries, and even better stuff, Lay's onion and cream and onion, sour cream and onion, potato chips, or even Doritos. Those are two of the most dangerous comfort foods I can think of, other than certain cookies. What happens? Well, think about it. How do you describe with words? First of all, I'm going to do it words in a general reaction, and you should know this. Oh, I better be subtle again. So how do you describe with words and a general reaction what happens when you eat a carbohydrate? Well, you chew your food. I think I told you when I was 2, my mother said, chew your food or you'll choke. And I found out before you swallow it, you'll choke. And I found out she wasn't lying to me. I did choke one time. I survived, in case you were wondering. But you chew your food and swallow it. What's in your stomach? Hydrochloric acid, there's water. And what's the key functional group in starch? An acetal. So how do you describe with words what happens when you eat a carbohydrate, a starch? You should know that's acid hydrolysis of an acetal. And from test number 2, and I'll write down acetal ketal, because that's how you learned it. You take an acetal or ketal, reacted with acid and water, what do you get back? You get back the aldehyde or ketone you would have used to make that acetal or ketal, plus the alcohol you would have used to make that acetal or ketal. And for those who want to, you could put a 2 there, but you don't have to. And you should know what happens when you eat a carbohydrate, how to describe that with words and a general reaction. It's acid hydrolysis of an acetal. And the general reaction, which you learned for test number 2, excuse me, acetal or ketal, acid and water, you get back the aldehyde or ketone you would have used to make that acetal or ketal, plus the alcohol you would have used. Now, what does that mean in terms of starch? Following reaction. And I could have also put HCl because that's the acid in your stomach. What would be the reaction product or product for the following reaction? And the answer is, if you look back here, what's starch? It's glucose linked together. So if I go the reverse way, what I will get is glucose. So in the cyclic form, but it's still glucose. And therefore, whenever you eat a starch, your body breaks it down to glucose, which is why that's the most abundant sugar in nature. Because our bodies, animals' bodies, break down starch to glucose, which our bloodstream carries along to various parts of our body to do whatever it does with that. Now I'm way beyond my knowledge of the human body and biology, but I know this much. So you should know starch plus acid and water gives glucose. Let's do another one. If you have acid and water, and remember in your stomach, we have hydrochloric acid, HCl, which is H plus as any acid, and Mother Nature. I always think of it as one of the wonders of the world. This totally astounds me. I have cells in my stomach that make hydrochloric acid. And there's water we've been drinking. I just was drinking. And what happens when you react sucrose, like you have sugar in your coffee, tea, or on your hot cereal in the morning or whatever, what happens when you consume it? Well, if we look over here, sucrose is fructose and glucose held together in an acetal ketal form, bonding. So eat sucrose and you get glucose plus fructose. So whenever you have something with sucrose sugar in it, you get back glucose and fructose in your body. Now, there's an interesting thing. This is my personal opinion, and I'm going to say it as much, but I think it's got some scientific background to it. A number of years ago, there were a number of concerned mother groups, which was a good thing, that went to the public and also the food companies and said, you've replaced all the sucrose in our children's food with fructose, high fructose corn syrup. And we think that's bad. That's calling us all the problems our children are having now. and they were saying fructose is bad for you. And I disagree with that, and I'll explain why. But here's the funny part. Well, it's not really funny. The food company said, all right, we hear your pain, and we're not sure you're right, but just to be on the safe side, we'll replace some of the fructose in our baby products, other foods, with sucrose. Well, think about that. If you have high fructose corn syrup and you consume it, you'll have fructose in your stomach and in your body. If you have sucrose, table sugar, guess what? You're still going to make fructose and now glucose in your stomach. So you're still going to have a lot of fructose in your body. If you look through the history, before they switched over to fructose, was there a lot of problems with things like autism and everything? I'm not sure, but it can't be just due to the fructose because sucrose makes it. And they played on, how should I say this, the mother's lack of knowledge of what happens in your stomach when you eat sucrose. Now, what I'm going to say is my personal opinion. So it's my personal opinion. But I think the main problem is, and trust me, unfortunately, I know from firsthand experience on my life, is the number of calories you consume. If you have something real sweet, whether it's high fructose, corn syrup that's making it sweet, or a lot of sugar, sucrose that's making it sweet, both are bad for you and help you put on weight. And being overweight causes certain medical problems. Luckily, I've had not that bad, but I'm still fighting, always been fighting my weight problem. If you haven't realized, I'm not a skinny guy, never have been, probably never will be. So it's part having knowledge of organic chemistry. You can look at things and say, well, I think it's the calories. If I lose weight, which I have one time back many years ago, I weighed about almost 65, 70 pounds heavier than I am now. And I had some serious problems. I took off all that weight and I still like to go lower. And a lot of those problems disappeared, like being able to walk up flights of stairs without. So that's a good thing. All right. Now, let me remind you, you should know how to describe with words and a general reaction what happens when you eat something that has a fat or oil in it. And what's the functional group in fats or oils? That's an ester. What's in your stomach? Acid. And because of water there too, we call it acid hydrolysis of an ester. And the general reaction you should know how to write is ester. And you learned this for test number 3. I could put HCl or just H+. You take an ester, react it with acid and water, you get back the carboxylic acid and the alcohol you would have used to make that ester. So for eating a fat or oil, that's acid hydrolysis of an ester, and here's the general equation. You should know how to do this. Hint, big hint. Next, if you eat a carbohydrate, you should know how to describe with words and a general reaction, what happens in your stomach when you eat a carbohydrate. And in your stomach, there's acid and water, so it's acid hydrolysis. And what's the functional group that holds carbohydrates together? The acetal. And what's the general reaction for acid hydrolysis of an acetal? You should know, and you learned this for test number 2, acetal or ketal, H plus, you could have put an HCl, but H plus is fine here. Acid, H plus and water, you get back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol you would have used to get that. And for those who must, you can put the 2 there, you don't have to. So you should know, ask when you eat a fat or oil, how to describe words in general reaction, and that is acid hydrolysis of an acetal, of an ester, I'm sorry, I'm getting ahead of myself. The functional group that holds things together in a fat or oil is the key functional group in ester. And here's the general reaction. Ester, acid and water, carboxylic acid plus the alcohol I would have used to make that ester. How do you describe words in a general reaction? What happens when you eat a carbohydrate? First of all, in your stomach, it's acid hydrolysis. And what's the functional group that holds glucose together? An acetal. And it also holds sucrose and fructose together in table sugar. And here you have an acetal reacting with water and acid. And that gives you back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol you would have used. You should know this. Now, interesting thing. See that? That's paper. Guess what? Paper is glucose molecules held together. I don't know about you, but if you try and eat paper, it's not going to keep you alive. Why? Well, let's find out. Now, it turns out everybody sees cellulose and starch on your screen. Thank you. Now, N here is large, real large. And for starch, notice how the oxygen bond is connected to the ring. The ring was flat on both sides underneath. I think that's called the alpha or beta linkage. I always forget. It's not an area I work in. And your body can acid hydrolysis to make glucose pretty quick. Now in cellulose, yeah, one is on top, and next one, it goes to the bottom, glucose. And this, I think, is called the beta linkage or alpha. I don't remember what it says, I'll look it up. This takes a lot longer to do an acid hydrolysis. One of the things I haven't done this semester is talk about kinetics. Kinetics is how fast a reaction goes and how to speed it up, other than saying, well, here's acid catalyst. I haven't talked about kinetics. It turns out when the linkage is in this way, between the two cellulose glucose molecules. And they're linked together by this linkage. That takes a long time to do acid hydrolysis. When they're this type of linkage, it's shorter to do acid hydrolysis. So that's the reason why you can't go out and start eating grass or hay like a cow or horse or elephant can. Now, I am not, and I will say this up front, an expert in animal husbandry, which means knowing about animals. But if you look at a horse, you look at a cow, or you look at an elephant, they have huge stomachs. In fact, and here, don't quote me on this, I think a cow has 4 stomachs. And why does that happen? Well, it turns out in order for them to gain nourishment and stay alive by eating their carbohydrates from cellulose, hay, grass, leaves, sticks, whatever, they need those huge stomachs to have the cellulose stay with the water and acid a long time to break it down to glucose. For us, Mother Nature gave us small stomachs compared to horses, cows, and elephants, and we have to eat starches that break down to glucose quite quickly. And now you know the secrets of Mother Nature, what happens in your stomach when you eat a fat or oil or a carbohydrate. Now later, before the semester's gonna end, I'll teach you what happens in your stomach when you eat a protein too. So you'll know the 3 main official food groups. And with that, I'm gonna let you out a whole 28.5 seconds early, maybe 30 seconds early. Shh, don't tell anybody, I'm being nice. And don't forget, on Wednesday, hand in your lab, that's due. On Wednesday, I will go through the fats and oils problem set. And tonight, I have my office hour if you have any questions about anything to do with this class. And with that, I'm going to say, gang gesund, see you on Wednesday. Don't forget, a week from this Wednesday, test 4. A week from today, I will be having my second cataract surgery on my right eye this time. This one's doing real good. Not to bring religion into the classroom, but I just did. Thank you up there, keeping an eye on me. Ooh, that was an awful joke. Sorry. With that, gang gesund. I'll see you either tonight or Wednesday. Bye now.